Okay, so welcome guys again to another video. So in this video, let's talk about this weak field and strong field feature, right? So if you have watched our previous video, like we have been talking about the octahedral geometry. So according to octahedral geometry, when a complex is formed, the 5d orbitals are going to change their energy structure like this: 1 2 and another 3. This is going to be dx squared minus y squared, and this is going to be dz squared. Here going to be dxy, dyz and dxz, right? So now what we need to understand is, let's assume, right, we have a situation like this. So we have a complex with chromium 2 plus. So this is a hypothetical, right? This is not this is just to explain this concept, right? So let's assume we have a chromium 2 plus complex. So if we have to write the electron configuration, it's going to be 4s2 3d4, I guess. For it's because 2 plus, we are going to eliminate 2 electrons, so we are left with 3d4. Now we have 4d electrons to fill. So here I'm going to fill 1 2 3. Now the fourth electron, I can either fill it up to here or here. How we can choose it? So you know the gap between the two energy levels, which is T2G and EG, is delta O, which we call as crystal field splitting parameter. Now there is a orbital. Here we have an orbital. It has a 1 electron. You know, in one orbital, if you are going to put another electron into this orbital, that both electrons cannot be in the same spin, right? Either this electron on spin on one direction and other one into another direction. So when I'm going to fill an electron into this orbital, there is a repulsion from the existing electron. So in order to put an electron into this orbital, I need to give energy. There is a specific energy barrier to pass in order to fill this orbital with another electron, right? This energy barrier, we call it as pairing energy, right? We denote it as EP. We call it as pairing energy, right? So now we have two energy parameters, right? EP or pairing energy, and delta O, which is crystal field splitting parameter. So now you must get the point, right? Now if I have to put my fourth electron into this place, then I have to overcome the delta O, because I need to put it on this electron, so it need to overcome this energy barrier in order to put the electron here. If I'm going to put the electron onto this existing orbital, then I have to overcome the energy barrier of pairing energy. So either case, I need to overcome an energy barrier. So which energy barrier is the lowest, that's going to be happen. So there are two cases, right? So let me clear this up. Right, so let's go on. There are two scenarios. The first one, delta O is smaller than the EP, which means that the energy barrier of this gap energy barrier is much smaller than the pairing energy. So if I want to put my electron either this place or this place, whether it suits the most. So if I'm going to put it into this orbital, I must overcome the pairing energy, which is much harder. Here it is much larger, right, than the delta O. So if I have to put it over here, then I need to overcome a much larger energy barrier. Instead of that, I can easily overcome this small energy barrier because delta O is smaller. So at this case, the electron will go and populate this orbital. But if the way is other way around, case number 2, which delta O is larger than the EP, now the pairing energy is much smaller, right? So if I need to put my electron over here, there is a lot of larger energy barrier which is hard to overcome. But instead of that, I can easily put the electron over here by overcoming this small pairing energy barrier. This is the case. So let me summarize this into much simpler way. Here we have the two scenarios. Let's say in this case, the first 3 electrons is going to be same, but in this 4th electrons, as you can see, delta O is much smaller. So energy barrier or the energy gap between those here, between these two levels are much smaller than the pairing energy. So I can easily overcome this energy barrier rather than this one. So the 4th electron go for here. In this case, that's not going to work because the energy splitting parameter is much larger. So energy barrier between these two levels is much larger. So it's hard to overcome. But the pairing energy is much smaller. So I can pair my other electrons with the existing orbital. In this case, the 4th electron will go to here. Like if I have to put another electron, like the 5th electron, just the same thing. Here's my 5th electron. Here, when I am putting my 5th electron over here, it's not gonna be overcome this large electron barrier. No, it will go to here. If I have to go for another electron like 6th electron, then in this case there is no other way. It just need to fill a existing orbital, so it will go to here. In this case, it will go to here. And then if I put another electron, it will go to here. And this case, it will go to here. Right? Another electron, let's say, I will put here and here. Likewise, right? In this example, when the delta O is much larger, delta O is much larger and the EP is much smaller, then it will go for that kind of thing. So these are the two main things you need to be understand. So there are two characteristics. So let me go back. Right. So this was the first thing we need to understand, right? So when our system is like this, right? When delta O is much smaller and pairing energy is much larger, as you can see, we call this as weak field. And in this case we call it as strong field, because like delta O is smaller. In this case delta O is larger, that's why we call it as this is strong field. Delta O is stronger. And the other most important thing is, in this case we can see the complex is at high spin. What does this mean? High spin. We call in this case it as low spin. Here, if I denote these electrons based on their spins, like all these spins are rotating on same direction. Let's say it's +1. So what is the net spin of all the electrons? It's going to be 4, right? +4 spin, the net spin. But in this case here, this is plus, this is plus, this is the same direction, but this one opposite direction. So the net spin is going to be +2, right? The spin is lower. That's why we are talking this. So we call this case as high spin, this case as a low spin. So this is the main things you need to be understand. Right? I hope you got that point. In the next video, let's talk about the magnetic properties.